So my name is Hadrien Calmet, and today my talk will be about the virtual population for the GCNN on the GPU to predict the respiratory system and flow features. I do this work with some colleagues of the Barcelona Supercomputing Center, Joan Calafel, Albert Perez, and Guillaume Mousseau, and we do in collaboration with the Jülich Supercomputing Center, so Rakesh Sharma, Mario Rüdger, and Andrea Linterman. So this work is part of a project, a GLSC project, involving different supercomputers which have a common interest. So there is the Spanish supercomputer, the Japanese supercomputer, and the German supercomputer. So the two first topic, you received some talk. The first one was the machine learning-based reduced order model for reconstruction of flow field. This was the talk of Rakesh. Then the other topic is physics-informed neural networks, so-called PINS, for prediction of flow field. It was the talk of Onishi-san. And my talk is about the flow prediction with a graph neural network. So it's more dedicated to the graph neural network and all the applicability that we can use when you have, for example, a non-structured mesh to use the neural network. So the motivation of the outline of the presentation. So first I will explain the motivation of this study, why we create this machine learning, then also how we create this virtual population of human nasal cavity, the computational aspect to run on these 300 virtual patients, then the analysis of the results with flow features related to physiological dimension first, then after the results of the graph neural network with some metrics. So from a medical point of view, the nasal resistance is a very good indicator of a patient breathing condition. This is why the doctor wants to know this value. So the nasal resistance is a pressure drop between the inlet and the outlet. So in the case of the nose is the entrance of the nose, so the nostril, until the nasopharynx, which is the throat. And with experimental science, you can recreate the geometry of a patient using the transparent silicone. And you plug in and plug out the entrance and the output, some water, and you put a settings with a camera, and you can recreate the flow circulation of this geometry. So this technique is called particle image velocimetry, also called PIV. Is a non-intrusive optical flow measurement techniques. So I used to study the fluid flow pattern and the velocities. So in other words, it digitalizes the flow. So experimentally to 3D. So with this, you have lots of information like recirculation, acceleration, constrictions, and you have, of course, the pattern of the flow. But it's almost impossible to measure the pressure drops for human nasal cavity from the PIV techniques. So this is why we think of creating the machine learning model, which is based on velocity field to predict the pressure drop. As you know, to create a machine learning, you need a decent size of patient, so decent size of data set, and we need geometry of patients. But it's complicated to obtain a lot of geometry of a patient for many reasons. One is confidentiality policy considerations in some hospital, then also the access to the hospital database. Then on top of that, you had a more complex layers, which is the tedious task of the segmentation. The segmentation, and when you transform scan MRI to geometry like this, like this 3-1. So you obtain the list of the nodes to recreate in 3 dimensions the geometry of the nasal cavity, for example. So this is the segmentation, and it's a long task because it takes a lot of time, and you need a knowledge of the organ that you want to segment it. So it's a tedious task. So for this study, we select only 3 patients. So the first patient is model A, is an average of 25 healthy patients. So we try to represent and having generalization global patient. The model B, which is Caucasian patient without any pathology, he had 44 years old. And the model C, which is an Asian patient of 40 years old with a slightly septal deviation. So we have small pathologies. So we will use the 3 geometry to create 300 patients using the scaling process, the random scaling process through a Latin hypercube sampling, through Dakota software, to create this virtual population. So for each patient, we create 100 patients. So in total, we have 300 patients. We use the scaling process to variate randomly the width, the length, and the height of each geometry, and we obtain this data augmentation. Once you have this 300 new geometry, you need to mesh them. So for the mesh, we create a quite refined mesh inside the nose to capture those features. Then also we put prisms layers on the wall to capture the gradient velocity on the wall. Once you have the mesh, we want to solve the equation and resolve at each point of the mesh the velocity and the pressure. So we use the in-house code that we developed in Barcelona Supercomputing Center called ALIA. It's a high-performance computational mechanic code, is a multi-physics and multi-scale. It's portable to many platforms. It's highly parallel because it was designing from scratch to run on supercomputer. And it's composed by different modules like the fluids, solids, electromagnetisms, chemistry, heat transfer, and Lagrangian particle, and so on. So here, in this case, we will use the fluids modules to solve the Navier-Stokes equation, and we will use the implicit large D simulation for the turbulence model. So we performed this 300 simulation on the Mare Nostrum, which is the name of the supercomputer that we host in Barcelona Supercomputing Center. And this slide is an example of the result that we have. This is for the patient 63. So we obtain some velocity information. Here we can see the velocity contour field. We compute also the map of the pressure across the geometry and the map of the wall shear stress. The wall shear stress is related to the frictions, and most of the time the doctors like to know if there is some discrepancy with the wall shear stress, because most of the time the friction could be related with some pathologies. All of this simulation are run with a constant flow rate, which we selected at 20 liters per minute, which is the average inspiration phase. So it would be like a snapshot of inspiration phase for each nasal cavity. So the first result, it's showing like this plot. It's let's say a physiological sensitivity analysis of the results through a Pearson coefficient, giving you the indice of the correlation, of the linear correlation between the input and the output. So the input here, as I explained before, is the variation, the random variation of the width, the length, the height of each geometry. And for each simulation, we compute the pressure drop of the model, the wall shear stress averaged on the surface of the model, and the energy flux of the model. The energy flux is the rate of transfer of energy. Give you an indice if, for example, there is a jet impinging on the mucosa or something like this. So this is why we want to plot it. So the values of the coefficient of Pearson coefficient, which is the value on the top of the plot, is ranging from -1 to 1. So it's meaning when it's -1 and 1, meaning that there is a highly correlated or highly inverse correlated. And when it's 0, it means that there is no correlation. So visually, when there is a slope well-defined with 1, it meaning that there is correlation between the input and the output. And when it's the potato shape, so a big potato shape, they mean that there is no correlation. So at the first glance, you can see that for the width, there is too high correlation related with the pressure drop and the wall shear stress. These two observations make sense because more narrow is the patient, more important will be the pressure drops than also the washy stress. For the rest, there is no clear correlation except for one case, which is the age of the patient and the washy stress. This is interesting, and it's not clearly evident, because this correlation tells us that smaller is the patient, more important will be the washy stress. Well, this remark need further investigation, and is not the scope of the talk, but it deserves more information, investigation. Sorry. So this slice is the GCNN architecture that we use and the distributed training framework that we use for this study. So we moved all the input and the training on the Jülich supercomputer, and we use a model that was published on the literature, and we adapt this model first because our data is on 3 dimensions, and the output was the drag, because the original model was to predict the drag coefficient on the foil, on the airfoil. So we adapt the model to put the velocity field in 3 dimensions, and the output was the pressure drop. And this is on the left, and on the right you see the distributed training framework that we used. And Jülich supercomputer, they developed an open source framework to run the training on the parallel way. So basically what you done is you distributed the data set. So each worker use a subset of each data set to perform the training, and one of the worker is the host worker, take care of doing the average gradient and update weight. Rakesh explained better this framework that they develop, but we use this to have a distributed framework for the distribution, for the training, sorry. Some parameters that we used, so is the width of the convolutional width, the depth of the graph convolutional, the activation function that we used was a ReLU. We used the top cap ruling with a ratio of 0.5 for the fully connected with 3 layers. With different values of width. Again, the activation function was a ReLU function. And for the loss function, we used the mean square error, and the optimizer was Adam. So this plot, this slice show the performance of the model, showing a quite good performance with the metrics, which was the mean square error. After 1,000 epoch, we obtain a very low value, around 0.0002. And on the right, you have the mean accuracy of the model, demonstrating high performance. This high accuracy is a relative error between the model output and the target output. And for the validation set, we obtain a very high accuracy, is 99.85%. Okay, so we train and we demonstrate. We want now to compare the value of the ground truth pressure drop, so pressure drop coming from the CFD results, with the predicted pressure drop coming from the model. And we plot the comparison. So we show a very high accuracy to predict the pressure drop for the training set and for the validation settings. But now we want to see what happens if we use a patient which is not included on the training set. As you can see, the error is quite important for the patient 1, patient 2, and patient 3. Sorry, for the 2 first patients, but at least for the patient 3, we obtain the 3% of error. So this means that perhaps this patient is a good generalization, patient-based for the model. But the results of the patient 1 and patient 2 demonstrate clearly that the data set is not enough, and the data set needs more patients to be capable to reproduce with a good generalization any patient with an unseen patient, which is not included on the training set. So for the future work will be, of course, increasing the size of the data set, trying to finding a patient from different type, different size, different shape, and also trying to analyze the generalization behavior of a patient and also from the model to have a more uniform, universal model. And also we want to try to adapt this model, so this GCNN, to only use in input the STL. So the STL will be only the list of the point of the geometry, and the output would be the air resistance, the pressure drop. That would be an interesting tool for hospitals to put geometry of a patient and having as output the pressure drop. But of course, we need much more generalization, aptitude skills of the models, and very robust to obtain a very low error. So thank you very much.